Hello, my name is Kevin, and today I'll present to you my results on a lab I conducted about black holes. The question we should be asking ourselves with this lab is how can we find the path of a black hole using the trajectory of a star orbiting around it? So for this lab, we were using a growth script code. To answer this question, we are given the mass of the star and the star's position during its orbit along the black hole. For this trajectory, we will place the black hole at the origin of our coordinate system. We will also make the assumption that the only force acting on the star is the gravitational force due to the black hole. So now we'll go into a more in-depth overview of this lab experiment to answer our question. In the initial condition and systems property part, I defined constants that will be useful later on, such as the gravitational force big G, the mass of the star star dot m, and the time interval delta t equal to 1 day, and the initial time at t equals 0 seconds. Our final goal is to use the definition of the gravitational force on a star, which I equated to net force on a star. This will be seen in the following slides. So on these slides is where I use the definition of the gravitational force on a star, which I equated to net force on a star. So from here, I can rearrange the definition of gravitational force on a star due to the black hole itself, or the mass of the black hole. This is where the calculation loop comes into play, and I start out by defining the initial and final velocity as well as the initial and final momentums. This way, I was able to calculate the final change in v or velocity and change in momentum. Using Newton's second law, I equated the net force to change in momentum over time, or dp over dt, and delta p over delta at. So then next I want to calculate the parallel perpendicular components of f net, which I did fix the parallel perpendicular components of dp over dt. As discussed just before, I now have all I need to calculate the mass of the black hole. I will also include some lines of code to represent the forces f net parallel, as well as f net perpendicular of arrows. Now let's talk about the observations I made from the output of my code. As you can see when I run my code, what I have on the slide shows the trajectory of the star in its orbit, as well as the three forces along the star's paths. It also prints out the magnitude of f net parallel, f net perpendicular, as well as the final answer to our question, the mass of the black hole. This can be seen in my glow screen when the code is run later on. The link will be attached. You can see here that the mass of the black hole is 1.88 times 10 to the 34 kilograms. So now let's have a closer look at the arrows. As predicted, the f net arrow in orange is centripetal, meaning that it's directed towards the center of the kissing circle, which in this case is the origin, the black hole. And the magnitude of f net parallel in magenta increases as the star approaches the black hole, and it decreases as moving away from the black hole. We know that the parallel component of the net force represents the change in magnitude of the star's momentum. We can therefore assume that the closer the star is to the black hole, the faster it travels. Regarding f net perpendicular, this arrow here is in blue here. It impacts the change in direction of the star's momentum. We can conclude from this that the star's trajectory is elliptical. All of these observations contribute to showing that black holes is in fact exerting an attractive force on a star. Now let's answer a few questions. First of all, what does all this mean? How do we use the rate of change momentum and net force? Well, the rate of change momentum, also known as dp over dt, and its parallel and perpendicular components are found thanks to the star's velocity, which is found thanks to the star's position. In other words, the rate of change momentum is calculated thanks to our physical observations of the star. On the contrary, the negative force on an object is calculated by summing all the forces acting on this object. For our situation, we cannot precisely know what all these forces are in this lab in the star. However, in this lab, because it was not possible to directly calculate f net, we first used our fundamental principle of Newton's second law, which means dp over dt, because dp over dt, or change in momentum over change in time, was something we were actually able to calculate. So now let's imagine a black hole whose mass we found was removed, and a different black hole was later placed in the same location that we discussed in the next slide. Now in terms of the black hole, let's assume the motion of the observed star remains unchanged and is affected only by gravitational forces of the new black hole. Will we be able to tell the difference? Will we be able to tell that this new black hole has a different mass and finds new mass? Because we base all of our research solely based on our observations of the star's trajectory, if the trajectory do not change, our velocity vectors, momentum vectors, and net force vectors will have all be identical. So no, we will not have been able to determine the mass of the new black hole. I will mention that this model could have been further improved. For example, closer to approximate derivatives, not calculate them. As we know, the smaller the time interval, the more precise the approximation would be. Therefore, I could have tried using a small delta t smaller than 1 day to obtain a better approximation of the black hole's mass. For example, minutes, seconds, and so on, or even a smaller day. To include fixes like experimental research, we were able to predict the presence of a new black hole as well as its position and mass simply by observing the trajectory of a star orbiting around it. Thanks for watching, and please tune in for future labs.